management and some science management, yeah. And his advisor is Fargo. Okay. And he's been working now at like Shale Hills for 4 years, 3 years? Fourth year. All right, so we're really looking forward to your talk.
All right. Hi, everybody. Thank you, Sue. I'm Warren. I'm a PhD candidate in the ecology program here at Penn State. The title of my talk is Exploring Differences in Forest Growth Across Shale and Sandstone Bedrock in Central Pennsylvania. As a brief overview here within this group, I really wanted to talk about what measurements, what forest measurements we are making out at Shale Hills. Give an opportunity to share what some of those data look like. And then with this audience, I wanted to talk about how does it compare to other forests that are growing on shale and sandstone ecology. And then for the second part of the talk, sort of intermixed with looking at those comparisons, I want to share some of the very preliminary data analysis that I'm doing, looking at the impact of lithology on forest growth. And the approach that I'm taking for my research is looking at this question of does lithology impact forest growth? The research that I'm doing is examining at sort of different scales. And one of them is using inventory data from across the state, and I kind of call that a larger spatial scale. And then another field study that I'm doing is looking at tree ring reconstructions of forest growth in the local region, and that's looking at growth over a longer time scale. So jumping into some of the data first here, what are we collecting at Shale Hills and Garner Run? So for some time now, there have been forest trees out in Shale Hills have been tagged and measured since 2008, and they're measured in periods of every 4 years. There's about 2,000 trees. It takes a big effort for everybody to go and find, measure, and make sure that the data match up. And at Garner Run, we have a similar style of forest measurement where we have 2,000 trees tagged and measured in a transect basis. And so far, there's only been one measurement period for that watershed. On here, I have 2,000 XX question mark because I'm curious within this group if we should be remeasuring those forests so that we have a more dynamic understanding of the way trees grow, or what the plan is for that. And from that data, we can get the forest species composition, individual tree growth measurements, and we can use that to look at the standing live above ground carbon in the forest using the same measurements. Ooh, wow.
Goes random.
Maybe. So we were just discussing leaf litter. Leaf litter is being measured out at Shale Hills for 2015, 16, 17, and it's ongoing. At Garner Run, it's being measured. It's been measured in 15 and 17, and it is still being measured. I just want to share some of that data. For these data and measurements, I have carbon accumulation over time. This is something that I've been working on in my field sampling, where at this point I have field plots out in Garner Run. I don't yet at Shale Hills. I have a proposal to ask for permission to core some of the trees and reconstruct growth at Shale Hills CZO, but I figured I would just share this with the group so that people will be more familiar before they get that proposal. We also have forest age data from both Shale Hills and Garner Run, and then many more measurements that a lot of students and DIs have been collecting over all the years. So the first data that I have to share here today is forest age data from Shale Hills and Garner Run. Shale Hills is on the left here, and on our x-axis below, we have stem diameter, and on the y, we have year of establishment, and this is first things you'll notice maybe is that there's a lot more data from Shale Hills compared to Garner Run at this point. Second, if we look at sort of the forest age, we have a cohort of trees that are established in the late 1800s in Shale Hills, and then we have this like second pulse of tree establishment that happened between the early 1900s and 1950s. And we kind of estimate the forest at Shale Hills to be about 100 to 120 years old. At Garner Run, the 11 trees that I have cross-dated at this point span about 110 to 70 years old, and the average forest age is 85. So already from this data, we can see that the intensively managed or intensively studied watersheds that we have at Shale Hills and at Garner Run are a little bit different in their age.
Are they both intensively managed?
Not managed, I meant mentioned, yes, studied. There's no intensive management on either of them. So, because everybody in this room is not a forest ecologist, I just want to introduce one of the concepts that we use to quantify forests in general. And we often quantify species composition and volume of wood by using basal area. Basal area is the sum of a cross-sectional area for all the trees in an area. So the sum of the wood in an area in black there is divided by the area that you're measuring in, and we usually represent that with a meter squared per hectare basis. This figure here is showing the percent basal area made up by different species in Shale Hill in black and Garner Run with the stripes on to the right of it. So this is 13 different species making up the forest, and that represents 97% of the basal area in the entire forest. And what we can see here is most on the left side of this graph for Garner Run, these species comprise most of that, and then there's a few different in Shale Hills. But one of the real takeaways is that a lot of the forest mass and or basal area are concentrated in oak species. In our region, we have mostly mixed oak forests. So just for context sake. So to present some of the leaf litter data that's been collected over these years, as I mentioned, there's one gap for the Garner Run at this point, and 2018 is continually being collected. But what I see in this is that the black bars, which are Shale Hills, there's really only a little bit of variation in the amount of leaf litter falling per trap. And then if we compare that thus far to the 2015, you see there's a lot of variability at Garner Run. But I think that's kind of to be taken with somewhat of a grain of salt at this point, because the intensity at which we're measuring this across the watersheds, it varies quite a bit. There's, I think, 108 traps out at Shale Hills at 54 sites or something of that sort. And then we only have 4 sites and 8 traps at Garner Run. So I think that variability could be inflated by the way that we're seeing. And I included this picture to remind everybody who's always working out at Shale Hills of some of the challenges that come with working in the field, and I like to call this incident one of the outliers for our litter trap. Structurally, the forest in Shale Hills and Garner Run have some similarities and they have some differences. I have these histograms up here to demonstrate sort of the distribution of tree diameters in a forest that we typically see. This pattern of reverse J shape is typical of an uneven or mature forest, where we have a lot of stems in the smaller size classes compared to there's a smaller portion of large trees out in the landscape. Within Shale Hills and Garner Run, the basal area, which is that metric of tree volume or tree area, is really similar in Shale Hills compared to Garner Run. So we have 24.5 for the Shale Hills in the most recent 2016 measurement, compared to 23. I would expect that to be a little different, based on what really I think is kind of interesting is that we have a much higher amount of above ground carbon stored in the forest that is at Shale Hills compared to Garner Run. So we have similar basal areas, which is the metric that foresters typically use to quantify the amount of trees on site. But after we've scaled up with allometric equations, there's a lot more carbon in the forest at Shale Hills.
One, could you just percentage, is that based on the wood density only or also tree height?
It's not based on tree height, it is based on tree diameter and the allometric equations that we use to predict biomass.
But you have basal area being the same.
Right. I have a schematic that'll help that come out a little bit coming up here. And because we have measured Shale Hills multiple times, we can come up with an estimate from our long-term sampling to say in 2008 to 2016, the forest is accumulating or has accumulated, this is an estimate, 0.78 megagrams per hectare per year of carbon in trees. And then again, without another measurement in Garner Run, we really don't have a comparison with this sort of data. So going back to Dave's question and how we get to above ground carbon, it's important to remember that species and tree size matters. So this is a graphic of the equations that are used to predict biomass based on tree diameter. I don't know if you can see that very well down here. This is just tree diameter or DBH. If you measure a DBH, we use these equations to predict how much biomass is in an individual tree. And then we sum that across the landscape and accordingly apply the proportion of carbon in that biomass. But one of the things that's important here is that between species and between tree sizes, you end up getting a different level of, a different amount of biomass. That's based on a lot of different things like wood density and biology, the way the trees grow. So here's an example where I have northern red oak and eastern white pine, and two of those trees that are 50 centimeters compared to a northern red oak and an eastern white pine at 30 centimeters. The amount of biomass that each of those trees is much greater, almost 50% greater between species when you get out here at 50 centimeters compared to 30. So the few trees that are out here on the distribution of diameter account for a larger proportion of the carbon stored in a forest. So moving forward, I want to use some of the data from the inventory to compare where do our CZO sites fit in the context compared to other forests that are growing on shales and other forests that are growing on sandstones across the Ridge and Valley in Pennsylvania. So from forest inventory data that's being collected from the Pennsylvania Bureau of Forestry on our state forests and our state game lands, I was able to overlay the plot centers GIS on the the geologic map of Pennsylvania and compile a database of 615 forest plots that fall either on shale bedrock type or sandstone bedrock type. For the sake of this analysis and the way that I've seen the CZO folks all talking about it, there was a lithology type classified as quartzite. I put that in with the sandstone category. And then I am working to sort of understand and model the way that forests grow from a variety of GIS-derived landscape variables. So in the data, one thing to recognize is that within Pennsylvania, this is a pattern for the eastern United States kind of at large, is that most of the forests on the landscape are in this 80 to 120 year age range. But within this data set, 85% of all forest plots that I have in my data set fall within this 60 to 120 year category for ages. So in this context, I have Garner Run here for that approximately 85 years and Shale Hills for that 100 to 120. In this context, Shale Hills and Garner Run are representative of the landscape at large.
I don't understand this pond.
So this
Is that bar for Garner Run?
is the,
Is that orange bar that is GR for Garner Run?
yes, I'm sorry here.
And then the bar with blue is SH?
Yeah, so on the x-axis, we have different age classes from inventory data. This is from 615 plots on state forest land. And the number of plots falling within that category is here. I am putting GR in Shale Hills. I guess I should go back up to here too. The pink or red represents sandstone ecology and the blue represents shale. And I want to put Shale Hills and Garner Run in context in comparison to other forests on the landscape.
But Garner Run is one of 130 plots
Right.
that are sandstone where all the trees are between 81 and 100 or the,
It is the inventory data is classified based on a few tree cores within a plot that tries to find a representative age for a stand. So the data that I showed from Garner Run, it varies between 110 and 70 years or something like that. And we bin them in these 20-year windows because it's hard to actually tell, like, this forest established in 1905 without knowing everything that was going on.
Garner Run and Shale Hills aren't in that data at all. Like
Right.
those, they are just marked as being that age. They're not in the different plots.
well, that's their age range? Yeah. If they were in there?
Yes.
So we have very representative, our sites are very representative of what's going on in the state, is what this shows.
So these two figures show the percent basal area of our plots at the CZO, the Shale Hill site and the Garner Run site, in relationship to the percent basal area of these species across the landscape as a whole, using all of the 615 plots. And really, it's, I think, one of the most important things to remember is that there's variability on the landscape and how forests are made up. And that most of the forests on the landscape across Pennsylvania are oak species, as they are at Shale Hills and Garner Run. But there are differences that kind of make Garner Run and Shale Hills unique in relation to the whole. And that if you look at black birch, there's a lot of black birch compared to the whole forest in the Ridge and Valley, or there is no red maple in our forest out at Shale Hill. So there's only like 8 stems compared to red maple. It's a very common tree. In fact, the most common tree by frequency in Pennsylvania. So just highlighting some of those differences and the way that we think about these forests in relation to the forest at large. So this is a plot that is summing the live above ground biomass or carbon. This is in carbon of forest from the inventory data set across different age categories. And because I'm trying to keep Shale Hills and Garner Run in context with this whole thing, there's really 2 things to talk about this plot. One, if we put the amount of above ground biomass on this plot in relation to forests of a similar age, Garner Run is about 85 years old. Within its category, it's actually bit lower than what we would expect from our averages across the landscape. And actually, the same thing goes for Shale Hills in this 100 to 120-year category, is that the amount of above ground biomass in relation to what forests growing on shale or sandstone as a whole have is lower. And then the second, and maybe the most interesting thing that I'm concerned with, is that especially within our forests that are most represented across the landscape, there's more biomass, more carbon being stored in forests that are growing on a shale bedrock in relation to a sandstone bedrock.
So do you want us to discuss this now, or do you want the flow of your talk to keep going?
I'm willing to discuss it. I think that actually is like what I was looking forward to most in this talk.
I don't want to disrupt your flow. Well, so if I understood what you said, the above ground biomass at Garner Run and Shale Hills is a little lower than compared to this statewide database for sandstones and shales, which maybe makes sense because Garner Run is a quartzite, which is almost pure silica, very little anything else. Whereas a lot of sandstones will have, more than just silica.
Right.
So it could very well be that you're an N member, which you might be able to tease out from your data because you said you added quartzite into the sandstone.
I have looked at that in the past, and all the quartzite is even lower. Like it's like a 1, 2, 3 situation in that regard. With this geologic map and sort of trying to find these broad patterns, I'm lumping them.
I'm just saying, I'm not saying you did anything wrong. And then for shale, Rose Hill Shale, where we are, is pretty carbonate poor. And a lot of shales in the state will have carbonates in them. I'm assuming, like we talk about calcareous shale when we get down into the lower part of Schaefer's Creek. I'm assuming those are all lumped into shale in your data set.
I would assume that as well.
Which means there's a lot more calcium in there, which I think can impact trees, right?
Yeah, definitely. I think that's great and interesting. That's why I'm excited to talk to people like you about this. That is a limitation in that within that geologic map, they have a primary lithology and a secondary lithology, and I'm lumping into categories. And the landscape is obviously messier, but I'm also thinking that with enough data, we are seeing these big patterns.
The error bars.
The error bars are standard error of the mean of each age class.
You might come in late. These are for 600 plots around the state.
615 plots. Yep. That are the bulk. 85% of those plots fall in this age range. So this is where the bulk of the data is. And this sort of isn't the whole story compared for the inventory. At Shale Hills and at Garner Run, I'm holding, we only measure trees 20 centimeters and larger at Shale Hills and at Garner Run. So I, for the sake of this talk, cut off the smaller diameter trees to represent apples to apples when we're looking at where Shale Hills falls and where Garner Run falls. These patterns are a little bit more exaggerated once you include the whole data.
So it sounds like you could pull out the plots that are in lithologies that are really most similar to Shale Hills and Garner Run, and then see where those circles lie.
That's totally possible.
Just to make you laugh, if you run BioMVGC with the parameters out of the box, I think you get about 600. Right?
600 what?
Megagrams per hectare.
Of carbon or biomass?
For the above ground biomass.
And is that full, is that like all soil and?
That's just running something like Shale Hills.
Okay.
Just
the vegetation.
And that's very, very different.
Also, sandstone and shale are probably two of the worst lithologies.
Compared to like a limestone or?
Yeah, with more nutrients.
What we see on our landscape though in context of forests is that most of the public land and forested landscape is on land that we can't farm, so the poor soils are the ones that we have our forests on. Okay, so with that data set, I'm trying to use models to understand not just, A and B lithology. I'm trying to understand what's driving the differences in forest growth on shale versus sandstone. And to do this, I've been compiling this database from GIS that links up all those plots in this figure to other metrics and pulling it out to model and try to understand what's driving these differences. And this is 7 of 13 in the way that I'm thinking about it at this point. I'm sure there's more that I could include and should, but I'm exploring modeling above ground biomass from these variables here. And I put this up just to show that the relationships across the landscape in a map format.
What's the compound topographic index?
The compound topographic index is the same calculation as the topographic wetness index. It's a measure of drainage on the landscape that considers how far a hill slope is, or how long a hill slope is from a certain point. So how big the area that can drain onto a point.
Got it. So it's not uniform across.
It's not,
variability.
but
is
at
much
this
smaller.
scale, it looks like it. If you zoom in, there's a lot of variability, but that doesn't actually come out when we plot it. So these are density plots, which are just smooth distributions, smooth histograms, basically, of the way that these variables fall out on the landscape.
Just in the Valley and Ridge of Pennsylvania.
Just in the Valley and Ridge in Pennsylvania, from the plots that I have in my data set. And they're pretty randomly distributed across the landscape, so I do think they're pretty representative of what we'd see.
What is a plot?
A plot is 814 meters squared, and I guess if you tally all that up, that accounts for approximately 50 hectares. So, been visualizing these in density plots to compare between shale and sandstone, how these fall out across the landscape. But what I've kind of been interested by is that a lot of these things, so compound topographic index, which is measure of the area that can drain into a forest plot or slope aspect, annual temp from a PRISM data set, or the 30-year average of precipitation from PRISM are not different on shale and sandstone lithology. So when we see differences in biomass on the landscape, it suggests to me that there is something inherently going on within that rock type that is driving the difference in biomass on the landscape. I have a few points here to also bring up. So for elevation, which I think everybody would probably expect in this room, sandstones are at a higher elevation in general than shales across our landscape. That just comes from the way that the material is able to weather. But I also tried to put Shale Hills and Garner Run on here. Like I said, I wanted to keep those sites in context with the broader normal. I know that elevation varies across Shale Hills, and I know it varies across Garner Run, but I tried to just put it in a representational difference. So it seems like Shale Hills and Garner Run are falling somewhere around the normal for elevation. Some of these I couldn't pinpoint because they vary so much on the landscape and they're derived from a 10-meter DEM. There's too much to sort of pinpoint. The scale at which we're looking at climate variables such as temperature and precipitation, Shale Hills and Garner Run have the same values for those using a PRISM data set. Some of the water or some of the soil variables that I pulled out from the GCIRCO database are interesting and that, and sort of unsurprising, that the percent sand in a soil in a sandstone is higher compared to the percent sand in a shale. If we're not breaking any, yeah, you're right. But I think that could play a role in how forests grow and the amount of water that the forests have access to in the soil.
What about that 30-year preset? That they look kind of different.
They do, like some of these shales get a little bit more precipitation.
Is that just higher
Sorry, yeah,
elevation?
it's sandstone.
Is that just higher elevation?
Probably.
Makes sense.
It could
And
be.
then that bump with the blue is that meaningful? Don't put your house on shale, it rains more.
Yeah, in the broader context.
Yeah, that could be why they have lower productivity or biomass.
Okay, so I've been using random forest to model above ground carbon storage, and it's in context for giving a talk about forests and bring up random forest. Random forest is a classification and regression tree model that is very black boxy, but it's able to handle large data sets and non-normal data and give you a sort of understanding of how important certain variables are to predicting, in this case, above ground carbon storage. So overall, I included these 13 variables in a random forest model, and the amount of variance explained is 35%, which is not super high, but for the sake of ranking these variables, that's what it is for now. Here I have just the distributions of these most important variables, and what comes up in this plot is that from top to bottom, these are the most important variables in predicting above ground carbon. Unsurprisingly, age is the most important predictor for above ground biomass, which you would expect because as forests get older, they grow more to a certain extent. But kind of surprisingly cool, what comes out in this model is that bedrock is the second most important variable in predicting above ground biomass. Now, where I'm sort of thinking and trying to tease this stuff out is that elevation is the second, and we see that elevation is sort of controlled by lithology too. They're interconnected. And then percent sand and percent clay, which are also sort of inversely related, all the way down the line here.
So if you lumped bedrock through percent clay into one variable, would that get you another 30% or something like that?
No, that's not really.
Oh, redundant.
They're so highly correlated. You've got
Right.
15% one, 15% another, 10% one. They're all the same variable.
Right.
Does a random forest though
Yeah.
hold one variable constant while looking at the other?
It's that you can work with non-independent variables in random forest.
So I know you'll get a fit, but if they're really all the same variable, are you kind of misleading yourself into thinking it's only a 2% effect?
So one of the ways that I'm trying to account for that is I'll remove bedrock from the model and I'll leave everything in there, and really it accounts for the same amount of variation. Or if I take elevation out and leave bedrock in there, it doesn't change.
It doesn't change.
Okay.
That's very good.
No, they're not redundant. They say it. So if you take bedrock out, does the percent variance explained by elevation change at all?
By very little.
Okay, so they're independent. That's what he's saying, that they're essentially independent the way the model is doing, the way that the analysis is doing. Because if you can take one out and the other one isn't changing, that is saying.
So random forest is really a rough interpretation, and I need to get better at that, obviously. But what I want to do with these variables as well is build linear models and use this as more of a model selection to do the type of analysis and interpret the way that Dave is sort of talking about.
So usually it's just filter among the sweet
I don't
variables.
understand. If you take bedrock out at elevation, it's still Isn't it, they're redundant? Seems to me that they're redundant. Like, if you don't need to know what the bedrock is, if you know the elevation.
But elevation would explain more variance if we remove bedrock and they were correlated.
So I guess maybe the question is too, what is some of the variance explained when you take out
Right.
Now,
elevation?
the whole model becomes what's
That says elevation.
So I'm going to move on to some longer term reconstructions of forest carbon in my field work. So in our local landscape, I've been sampling forest plots on north and northwest facing slopes on the Tuscarora quartzite and the Rose Hill Shale, in Stone Valley and in Rothrock. And these are the same hill slopes that Lily Hill used for her research in the past. Just for the folks that have been around for a while, will remember those two. So I'm trying to come up with 5 sites for lithology and sample 3 fixed area plots at each site at least. And this schematic is here to show that, yeah, within a 10-meter radius circle, we're sampling all trees of all species up to a 5-centimeter size class. And using tree rings, so we go out, we establish these fixed area plots. All trees are cored 2 times in each plot. And then I'm trying to just give you a little primer on tree ring methods here. Tree cores are mounted onto these wooden mounts, and then they're sanded with progressively fine grit sandpaper all the way up to like 9 microns. You really have to polish these things up. And then in the lab, I'm counting and measuring the number of rings and measuring the width between rings. And I'm using that to reconstruct stem diameters through time to apply those allometric equations to understand how carbon is changed on the plot. So this is a picture of all the cores from one plot that's growing on a sandstone site. There's like 18 trees cored twice or something of that sort. They're measured twice because I'm reconstructing what we assume to be a circle, and they're not perfect circles. So I'm averaging between the 2 cores. This plot here is a spaghetti plot, and it's just showing a variety of things. But one, how long back in time each of these samples goes. So they are not all represented the same, even though we might understand this plot to be established in 1900. And then it shows the variability in ring width across time. So within this framework, I'm trying to understand how these forests have got to the point on the landscape today in which they are storing the carbon that they have. And this is just an example of 6 different plots from tree ring reconstructions that have been cross-stitched to invest in our ability within our local landscape. And interestingly, in this context, we see that the plots that I have sampled and dated at this point, the sandstone sites have more above ground biomass than the 2 sites on shale, but it's only 6 sites, and I'm not putting that much weight on that at this point. But what is pretty interesting is that it definitely seems like the slope of these lines is somewhat different. So there's something controlling for different productivities across the landscape.
I think the difference between these sites and the others is the age. Here you have old sandstone sites and young shale sites, whereas in the Shale Hills Garner Run go the other way.
Yeah. So, sort of, yes. On these 2 figures, the 2 blue lines there are 2 plots from the same site in Stone Valley and 2 plots from the same site in Rothrock. If you look at the annual change in carbon between the 2, they sort of vary within the same scale between almost 0 to 2 megagrams per hectare to a very similar level of productivity just from these two plots. This is very preliminary. I'm not going to say that it's overall the same. But yeah, there are different ages in the stands, but it seems like so far I'm not detecting differences in productivity from these plot-based scenarios. One thing I'm excited about and finding pretty interesting is that the way that these lines are following and matching up on a site is pretty tight. And for a tree ring reconstruction, that would suggest probably that there's a climate control on forest productivity. They're responding synchronously. So not as this data set becomes built and developed, well, we'll know more, but it would be really, what I kind of hope to do is take a graph like this and then model it with climate variables for sites growing on shale and sites growing on sandstone, and trying to figure out if the forests are responding to different things, or if they're responding at different magnitudes to, for example, precipitation or temperature.
I'm a little confused between the two different plots. So the left-hand side is 2 trees, or 1 tree in 2 spots, and 2 different forests. What's on the right-hand side?
Okay, so yeah, thank you for that question. The left-hand plots they're all plots, so it's all trees within a fixed area. Could be anywhere from 18 trees to 52 trees. And this is their carbon accumulation through time based on the sum of all of their growth. On the right, you'll notice a different time scale. I'll get to that in a moment, but that's just a change in a year of this graph here. So one of the issues, or just the nature of dealing with tree rings, and that's the reason I have 1970 to 2010 only represented with this change, is because we get these spikes and bumps in the data set as we go back in time. Really, that's just a relic of the record's not there for the tree ring. Either there's rot in the center of a tree, or there is only trees that are a certain age, like they've established at different time frames. So in this plot, that spaghetti plot is this line, and it's pretty solid, but we do see some bumps. And those correspond to probably like pulses in tree recruitment, where they're now representing themselves in the data set where they're not in other places. So I intend to have 3 lines per site for 5 sites across our landscape and model this forest growth with climate variables to see if on the underlying bedrock there's something about climate, like moisture, that's driving differences in growth that would lead to these patterns across the landscape of differences in biomass.
I think also a really cool thing to think about is that, we have these, what we perceive as a constant, from the inventory data, for example, we have this estimate of just under 1 megagram per hectare per year. But from these data, you can see, for example, 1980, it's a really low, a year where very little carbon was taken up by these trees. Yet the years before and after, you have, up to twice as much being taken up in the forest, not in individual trees, but the whole stand. So it's a pretty large amount of variability. That,
yeah,
to understand why they start, scaling that up to exchanges and whatnot.
So when you talk about modeling, you're mainly thinking about the random forest type stochastic modeling, or are you talking about a more mechanistic approach?
I think when I get to a point where I have a data set that's large enough, we can use like general mix model to hold certain variables constant and others.
Yeah, that's still stochastic modeling. What I'm thinking about is something more ecosystem like biome VGC that actually says, based on this kind of weather, this is what we predict photosynthesis to be, And this is what we'd expect carbon gain to be.
Are you advocating for more modeling? I know you are.
I'm advocating that stochastic can only take you so far, whereas if you could actually use the mechanistic modeling, we can get more insight perhaps in how, because a lot of these relationships are non-linear, and most of these stochastic models are usually talking about a linear effect. And so there could be some advantages to using something like the weather data in a more mechanistic way.
Definitely willing to explore that. So
recruitment is still in there though, right?
recruitment is in there, but mortality is not.
But you explained that sharp change as some funny effect of recruitment. How do you, those abrupt changes, like 1970 in the lower blue curve,
Right there.
and you don't use this stuff before 1970.
Okay, so yeah, what I'm finding is that
chop it off?
most of the trees are represented up in, like if you go back in time to 1970, that's the time when what we see on the landscape today, we have a good record of.
Most of the trees are in there.
Right. We start to get a lot messier as we go further back.
So if you have 80 or 90% of the trees, then you keep going. But if you only got 15% of the trees.
Yeah, I need to figure out a way to like devise a plan that makes sense for that, or based on the diameters of the trees that are in that data set that are not represented, to find a way to model what they would likely be producing.
What is the frequency of heart rot in your?
It varies by species. Off the top of my head, I don't.
And by plot, there's certain plots that you have a tendency to have a heart rot.
Right.
Well, species.
Heart rot, like the trees are rotting from the inside.
It's just a word I never heard, but
Also,
I could
yeah,
have used it many times in my life.
Black birch is a species that has a lot of rot in the center. So, and is also very hard to date and cross date. So there's a lot of challenges associated with this as well in the lab.
So remind me, how is 80 years about all you've ever going to see for black birch, or are you going to find?
There's some old ones out there too.
What?
There's some old ones out there too. Like I think the oldest black birch is like 325 years
Oh,
old.
is that right? They live that long.
It's the oldest tree in my data set, goes back to like the mid to late 1700s.
But they can live.
There are some weird old pockets of forest that have been left out there. So that's the data that I have to present for today. Of course, we can talk about other questions and whatnot too. If there are any.
Thank you, Lisa. So why is there more above ground carbon on shale than
Why do I think there is? I think that it has to do with the accessible water to these forests, that sites that have sandstone on their geology are maybe a little bit more taxed for water. I think that there could be, we saw some differences in elevation that come out from the data set that I'm not picking up differences in temperature and precipitation on the scale of climate that I'm looking at using PRISM data that might make a difference. I think the soils might be deeper on shale.
At least on our. But your tree rings show that the sandstone has, so far, sandstone has more above ground carbon.
Right.
Do you,
That's a small area. Once the samples, I think that that's like too easy to draw a conclusion at this point.
But across all the plots, the inventory, you're showing more carbon in the shale zones.
It's just that plot when we include all the trees 11 centimeters above from the inventory, and the differences is even, they come out larger.
So those differences are significant, I take it.
They are. I did an analysis of covariance where I looked at forest age, and then, yeah, they are different. And in a lot of cases, it's like a 20% difference.
I think one of the things that struck us just in terms of, global change, forest ecology is start looking at some of the projections for impact, for example, of climate change, which gets a lot of attention as it should. This difference is as large as what you get from projections of how climate affects forests, and yet sort of not really taken into account very often in terms of perhaps modeling, if you're looking at things like modeling carbon.
You also started with 2 histograms, one for the shale and one for the sandstone. And they were different. Why were they different?
Within our local, like, Shale Hills Garner Run thing, or?
I think it was the one that you had before this.
Besides
The age of trees.
The size of trees.
Yeah,
Size of trees?
Yeah.
They aren't different. This is a relic of including the new stems that need to be added into the data set from Shale Hills of smaller trees that have grown into the cohort. That'll bump up as soon as that data gets entered into.
So you don't think there is any difference here, basically?
I do actually think that there's some differences. I found that there's actually more stems, more trees growing on forest growing on shale than there are on sandstone. So there's a higher density of stems, but there's just more small stems on forest growing on sandstone compared to shale.
Oh, I thought it was the opposite.
Yeah, it's more on sandstone than.
Oh, sandstone.
Yeah, sorry, you said.
Sorry, I gotta get
Wait,
that.
so
That's-
what did you say? You said more trees, more, so what was it?
more stems per unit area
Yeah.
growing on sandstone compared to shale
So there's just smaller.
Across all plots.
across all sides.
Because this looks like young forest versus old forest to me. Like the one on the right looks like it's still self-thinning and there's a lot of small trees, they're gonna die. The one on the left looks like it's farther along in age and self-thinning. Is that totally wrong?
I think it's wrong because what we expect to see is a continual recruitment. Like this always stays high, but as trees get larger, more of the large ones die because they're competing or they get old.
But I think what Jason's saying is if there is a little bit more of the drop in the small stems recruitment at Shale Hills than at Garner Run.
I have a different figure too, sorry. This is that same plot using all of the stems in the inventory database. So that is, I think what you were just saying is a little bit more pronounced in this scenario too.
I don't know, I can't move that quickly between the two.
Sorry. That's the same reverse J-shaped distribution for all stems on shale and all sites on sandstone. And this is a relic of the fact that there's more plots on sandstone, but also that there's a higher density of trees.
So if you took stands in that 80 to 120 year age class, is this the plot you'd see?
Yes.
So I'm curious about, you showed no relation, well, your CTI was flat. And we've been working on Shale Hills, studying what we think is a significant difference in biomass at the bottom of the valley ridge tops. That sort of structure should show up in the CTI, shouldn't it?
It may.
And so what I'm wondering is, are we fooling ourselves?
I would think if you systematically sample, like maybe the variability in the landscape, like at a valley bottom versus a ridge top, I would expect it to come out when we have 615 plots, but it's not. But I bet if you sampled it across a transect on a hill slope, that it would probably be really important. hard to make.
Are the plots that you're using for this like big? Right.
Like 10 meters, right?
They're 16 meters in
That was
area.
just- Okay.
And I've calculated the CTI based on a 10 by 10 DEM, so it's really small.
Yeah, that seems surprising.
So you're, what
I'm
you
scratching my
said
head on
was that if you look at your plots, you didn't see a difference between ridge top and valley bottom, is that what you said?
No,
But if you did it across the transect, you would see.
I think that we went out to like Shale Hills and went from the ridge top and we had a point. Depends on how scale is complicated in that situation. Like we'd have a different CTI at the ridge top and the valley bottom, and we would also have a different biomass. Higher in the valley bottom for biomass and lower on the ridge top.
Because I don't know exactly how the CTI is computed either. Could it be something about that?
Yeah,
That's what I'm asking. Is it really
I don't
the,
have the actual equation for it.
yeah.
Is this
seems like a big
CTI
word.
calculated at the 10-meter scale? Well, that's what it is.
That should be okay.
Well, the
Yeah,
DEM
because
is
then you could have a flat part of your ridge,
aggregating it.
right?
But what
It's
if
the
it's,
scale of the curvature.
what if it's the curvature and the curvature could be this way or this way and it's the same CTI? But those could be very different for the hydrology.
I suspect that it's some indication of like where you are in the contributing area. And so it's going to be one end member is a ridge line, the other end member is a valley. And how linear that is between those values for the ridge line and the valley, a lot of times it's can be like highly nonlinear index that, you know, what the range of the CTI is of what we would call a ridge or side slope or valley. So it might be tricky if you're just looking at the distribution of those smeared over 10 meters, smeared over whatever the plot scale is, plus whatever, you know, the sampling bias of where people put the, you know, where people study these plots. So I can imagine it's not, might not be the ideal data set for probing the role of landscape.
One thing you could do is, since you know Garner Run and Shale Hills, and then you also have the plots that you're sampling, which have also been controlled, just go ahead and look at the CTI for landscapes you know. Just start there and see what is the CTI capturing on that.
That would be a
See
good.
if it makes sense.
See if it makes sense, and see if you're all of a sudden getting the valley bottom and the ridge top having the exact same CTI, like you said, because
Right.
it's due to the concave and convex.
Yeah.
And then go from there, and if it's really, and it might be like what Roman said, that it's too much smearing of too many things, and it's just not, can't capture what it's meant to capture. I mean, I guess it would be great to have any input on how, do you have any suggestions on other ways to capture that dynamic of the.
One other point is how accurately are these plots referenced, right? In terms of like, if this is somebody with a handheld GPS, that's plus or minus 20 meters.
They were
So-
they have to be relocated by field crews, and they didn't scramble them, so I think they're pretty accurate, but.
Is it the forest inventory?
Yeah, this is, the Bureau of Forestry and Game Commission.
Yeah.
Do the inventories include leaf area index? I was wondering because your hypothesis seems to be about water. And maybe if that's true, then the biomass is controlled by the leaf area that can be sustained. Water.
I don't think that in the inventory data set they measured LAI for Whitehorse. We maybe could find it from satellite imagery or something of that sort. That would be.
So the other,
Water thing, I think you need to think about ways you can use the soil, the SERGO data to get it at that, because the sandstone soils are deeper, like at Shale Hills, but they have large, they have lots of big rocks in them, so the total amount of water storage could be lower, and so I think it'd be good to pull that out if you're targeting water. Did you do that? So I was gonna ask.
Cheng, does that make sense to you in terms of water availability between sandstone and shale?
So from the SERGO database, this is a available water capacity, and I'm not sure that within the SERGO database how well they're doing it across a landscape scale, saying what some of those variables might be. So they didn't measure the soil. They didn't measure percent sand at every point in the database, right? It's extrapolated.
And I'm not worried about that part, but yeah, it depends how they calculate it with the water.
should ask Chang what he's learned already about this from our 2 sites.
The sand percentage from here, or if we say the frosting, I would say the sand lithology will have larger frosting and higher sand percentage, which holds less water compared to the shale.
Because it drains faster.
Yes, yes.
Okay. Sounds consistent.
So Warren, do you have any LiDAR data for these plots that you could get tree height, or do they give you tree height? Because a lot of times, like what we see both at Garner Run and Shale Hills, is tree height can be a more sensitive measure of, you know, the degree that moisture is not limiting and other things are. And partly these elementary equations don't take into account tree height, which also could be problematic. And so if there's any way you can get it independently, because they did do LiDAR of the whole state.
Yeah, those data exist.
Yeah.
You have to process the point clouds yourself.
I don't know if Christian could just feed in some of that information for you.
Although the height's gonna emphasize the difference even more. I mean, right now they're.
Sure, but it might
Yeah.
help pull out some of these things that you're not capturing with just a basal area.
I think that sounds great. I'm skeptically scared to take on a data set that is at that high of resolution and over this amount of area. If it's just like a similar file to DM, I can just pull out all the information and have it in the data set like I have with other things. Yeah, it could be neat.
Probably Doug Miller and Kristen Vicker, people to talk with about what that would involve.
I think if you gave them the coordinates, they might be able to pull it pretty fast. I don't know for sure.
So I'd say it's easy to do for 1 or 2 sites. For 600 sites that are spread out over the entire valley and ridge, it's going to be a little bit more of a computational challenge because, you know, you could either set up something where you're just extracting the tiles for the plots that you're looking at. It would be a considerable effort.
If the
It would be worth it if this is really something that you want to test a hypothesis about, like, you know, picking a few characteristic shale versus sandstone sites. It would be an easy thing to measure to see like what the data look like if they're telling you if there is a lot of variability and height is a function of biomass or something like that. But it would take like a little bit more of a dedicated data mining effort to do this over 600 or so plots.
Are they just like raster data
So
sets?
this is I don't think that so Pennsylvania State LiDAR produces a raster version of the LiDAR data set that is there. They don't produce a rasterized version of the unfiltered data that has the canopy height. So you have to go back to the point cloud data, and basically the filtering is it's hit or miss in terms of how much hand-holding you have to do to actually clean it up so that you're just getting the data points for the canopy and not like power lines and things like that. So there's another step of like dealing with just like the data, because this is already 10 or 12 years old, and it's standards for how they classify the point clouds and things like that. There's some things to do, but it would involve taking the point cloud data and then processing that. And there's automated ways of doing that. Once you sort of figure out, you know, just with like one tile, you can pretty quickly figure out whether this is going to be something feasible or not. But then it's just a matter of figuring out like, okay, how do I automate the downloading of the tiles that I need rather than dealing with the terabytes of data for all of the valley and ridge. So it was just doable, but would require sort of sitting down and thinking through how to work with this data.
Can you get back to the very beginning of your talk? So there's 2 pulses of age in Shale Hills. Just tell me about that.
Well, it wasn't there, but maybe somebody cut the forest partially and it opened up the canopy and trees were able to recruit. Maybe.
Well, don't we know that it was harvested twice or something?
Yeah, I think
Can we map that knowledge onto this somehow? I mean, like, I don't know anything about these kind of data, so I want you treat people to talk to me about what does this tell me?
there could also be, maybe there was a bunch of chestnut in there. The timing is right, I don't know,
Yeah,
if it's been on the ridge,
Can you
but.
tell when the 2 cuts were? Is that obvious?
Oh.
And between 1900 and 1950, was there a cut conceivably? Is that,
Conceivably.
it's obvious. Like,
No, it's not obvious. I mean, it's, I don't know exactly when the cut was estimated to happen. I feel like I read it was like in the 1930s or something like that. I can't quite remember. So.
But I mean, is that one explanation?
Yes, absolutely. That is one explanation.
And then-
Chestnut
then there
mortality.
could have been one between 1850 and 1900 or something? Okay. And then what was going on over at Garner Run?
I mean, they just like, and this is only 11 trees and it'll be more trees.
Data to see.
But when it does come out, I would think that this flat line would suggest that they removed the whole overstory and the forest established.
Around by 1900 and then.
Say it again?
They cut everything, clear cut,
Okay.
around like 1910 or so. And then that's why all the trees are able to establish. They weren't cut. Everything that would have existed here was removed. So that I would think about that, and most of our forests in the region.
Do we know anything about the distribution of chestnut on shale and sandstone?
I know a little bit from the data set because they do measure chestnuts that are big enough and that it's more prevalent on sandstone sites.
We're not talking about chestnut oak, he's talking about.
Chestnut, and chestnut, very chestnut. But that, it was probably more on sandstone than it was on chestnut. From the data that I see. But that's like sprouts that are out there in the plots.
That's also the natural history, the knowledge of it is that it was on ridge knobs. I mean, it was more commonly on ridges than toe slopes. I mean, it can grow and.
Then you had a histogram that had some species data on it, and it looked like there was a difference between, I think it wasn't this one, I think it was, keep going. Is there another one?
Yeah, inventory compared.
Is there a species difference between Shale Hills and Garner Run that I can hold in my head?
There are between Shale Hills and Garner Run, yeah. So one I pointed out is that there's a lot of black birch at Garner Run, and there's almost no black birch at Shale Hills. Chestnut oak is almost equally represented. There's a lot more red maple, and there's none at Shale Hills. Okay, I'm trying to put this up to have the comparison between Shale Hills and Garner Run, but then also the comparison to the whole forest.
And hickory, oak, and hemlock. Hickory, white oak, and
I know,
hemlock.
yeah, right?
And sugar.
Sure, none of that at Garner.
So all those trees down there are not at Garner Run?
Yep.
Why?
Probably because of their preference for more moisture, not Virginia pine, take that out of there. White oaks are. I would think sugar maple because of the amount of calcium from the bedrock that is in the soils at Shale Hills versus Garner Run. That's one factor. It's a little older, so maybe you could have that. I mean, what you see here from the larger data set is that sugar maple really doesn't even occupy sandstone sites, so there's that. Eastern hemlock. I don't know why we're not seeing it at Garner Run. It's definitely out there in some of my field sites on other places. Could be because the forest is a little bit younger.
Remember those the transect maybe just was outside of where hemlocks are in the valley bottom. Because, we just put the 3 linear transects, ridge top, mid slope, and toe slope. do you think it could just, the hemlock could be just a little bit closer to the creek?
It could be, or what I actually see in my field sites is that the hemlock is almost.
Oh, the
it
ridge
doesn't
top,
back
yeah,
up, like-
and there's just no hemlock on that ridge top. A lot of that hemlock has died from woolly adelgid. I mean, that's like the first populations to die are the ridge top environment. I'm really surprised by the hickory being, there being no hickory and Garner Run. That's surprising.
There might be like 1 or 2 stems in the whole basin.
So one of your possible hypotheses is that you're less diverse on the sandstone sites because of calcium and water limitations.
Can you repeat that?
You're less diverse on the sandstone sites
Yes.
because of calcium and water limitations on the sandstone.
Maybe not that specific, like exclusively calcium, but because of resource availability in general. Maybe. It's a complicated one to pull out in ecology.
Are they less diverse or just have different species? To me, they look like they have the same diversity and a different species.
There's more species per unit area on shale forest than there are on sandstone in the data set. Yep.
And is it because you're picking up more music species on the shale? Is that the principal factor?
I would think so.
Like sugar maple?
There's that like wet environment, yeah. They can't tolerate dry. And it definitely is a tail, and like there are many species that are very low representation, but.
Right. Yeah. So this is the basal area of 97% of all the forests, and this is the basal area from the larger data set of like 80 and 89. So it's like 80% of all the trees are these species on shale, and 89% of all these species are on sandstone. So it's a little different too.
Okay, maybe we better thank Warren again. That's late. Do you want to tell us what you're going to talk about on 23? Advertise it for yourself.
I think that I will probably talk about introducing my research since I'm a new faculty member. So I'm going to talk about Candidate Ecological records and how they pertain to what you guys do in the CZO community, mostly in the tropics.
Thanks. Thanks, everybody. And thanks to Jennifer and Kathy for doing your technology work.
Like,